Good afternoon, students. In continuation to the previous lecture of unconventional manufacturing process, which we have dealt in the previous lecture, we are going to now proceed further. In the previous lecture of unconventional manufacturing process, we dealt with the unconventional machining process, classification of unconventional machining process, that is mechanical, thermal, electrochemical and chemical. After that we classified and got about the various processes which are to be there in the various classification, broad classification. After that we discussed each mechanical machining, thermal machining, chemical machining, electrochemical machining. Now today we are going to discuss about the mechanical non-conventional machining. In this we have actually three topics, that is water jet machining, which you can currently see on the slide. Then there will be abrasive jet machining, and then there will be abrasive water jet machining. Now let's start with the process water jet machining. Now water jet machining, as I have already told in the previous lecture, what is water jet machining? Water jet machining is also known as hydrodynamic machining, which uses water only as a cutting fluid. Use a fine, high pressure, high velocity of water directed at the work surface to cause the cutting of the work. Means high pressure, high velocity of water is directed to the surface, whatever is the surface where we have to do the cutting work. Here you can see in the diagram, see there is a source of high pressure water. This high pressure water enters, which passes through a valve. This is one valve that allows the water to enter the delivery pipe to the nozzle, and it doesn't allow the water to go back. So once water enters, there is a nozzle, and the function of nozzle is to accelerate the water at a very high velocity. This high velocity water, when impacts the material in the form of a jet, with a due course of time, it creates a cavity in the workpiece. Here you can see the cavity in the workpiece, and the excess of the water which has been used passes through the drain passage. You can see it in this blue one is the work, this is the water jet, and this is the standoff distance, very important parameter which we will be discussing in further slides. This standoff distance means the distance between the nozzle tip and the workpiece. Now see what would be the nozzle diameter. So in water jet machining, what we are using, only water at a high velocity from a nozzle is used to cut the workpiece. The nozzle diameter can be up to the range of 0.1 to 0.4 mm. Pressure will be up to 400 megapascal, such a high pressure. Velocity up to 900 meters per second, and the velocity will be up to 900 meters per second. Very high velocity fluid will be impacting the workpiece, and it can cut the hardest material also. Fluid is pressurized by a hydraulic pump. There is a hydraulic pump. You can see the source over here that has been shown. Source of high pressure water, that is hydraulic pump. Now what are the important process parameter in water jet machining? Standoff distance. Standoff distance, I have already told you, the distance between nozzle tip and workpiece is known as standoff distance. Is small to avoid the deflection of the fluid stream. That distance cannot be very large, that distance, standoff distance, cannot be very small. That we will be discussing in further about abrasive jet machining and abrasive water jet machining. We will be discussing that. I will show you that how standoff distance affects the cutting parameters. Nozzle opening diameter affects these are the process parameter. If you change any of the process parameter, standoff distance, nozzle opening diameter affects the precision. If the larger is the diameter, larger will be the distance of the jet. Water pressure, if water pressure is low, it is not possible to cut the material. Cutting feed rate, the velocity at which water jet cutting nozzle is traversed along the cutting path, means this nozzle has to, this is the workpiece, if this is the nozzle, then it has to travel in this direction. This is called as traverse direction, either this direction or this direction. This is called the traverse direction. If one nozzle is being pointed at this point, then this is called as the traverse direction, or this may be called as traverse direction if the cutting is in this direction. The cutting feed rate means at which rate you are traveling from center point or from one point to other. At which rate, what is the speed, like it can be of 2 meter per 10 minutes or 1 meter per 10 minutes. This will be the called as feed rate. Now coming to the next slide. Now introduction. Now water jet machining, what we use water. Now there is another process that is called as abrasive jet machining. What happens in abrasive jet machining? In abrasive jet machining, abrasives are used. There is no water, but abrasives are mixed with gas, and is a form of cutting abrasives are mixed with the air, high pressurized gases or air, and these are focused to the workpiece through the jet, and these abrasive particles, you can see the black spots are abrasive particles, and this will hit the workpiece and there will be removal of material. In AWJM, you can see the first point. In AWJM, the material removal takes place due to impingement, yani hitting, means hitting of the fine abrasive particles. Impingement of the fine abrasive particles. The abrasive particles are typically of the size of 1,000 of a mm, means 1 by 1000 size of the mm, that is 0.25 mm diameter, and the air discharges at a pressure of several atmosphere. The pressure is very high. You can see here in the diagram. Here it is written that air particle stream, means these particle and air is injected in an is made to pass through the nozzle, which accelerates the abrasive particle, and the tip of the nozzle is made up of tungsten carbide or gem, means hard material is used to make the nozzle, because abrasives can itself damage the nozzle as well, so that material needs to be hard. Now you see the velocity will be approximately 150 to 300 meter per second in abrasive jet machining, and the width, or the kerf width, we call it the kerf width, will be almost the width in which this nozzle will be focusing is 0.3 to 0.5 mm, much smaller than a conventional machining process. And standoff distance, you can see the standoff distance is approximately 0.8 mm. So in abrasive jet machining, what we are using abrasive particles and air or gas. Now what is mechanism of abrasive jet machining? How does abrasive jet machining work? Abrasive particles impinges on the work surface at a high velocity, and this impact causes tiny brittle fracture, and the following air or gas carries away the dislodged small workpiece particle. Means abrasive particle impinges on the work surface at high velocity, it is impacting at a high velocity, and this high velocity particles, when impinging on the surface, they are creating a brittle fracture, tiny brittle fracture, and the gases coming just after the tiny particles are taking away the removed particle from the place, so that next particle can hit and create a cavity. You can see in the next slide, you can see in the figure, what is mechanics of AWJM. This is the abrasive, which is, and this is the workpiece. This abrasive grain is cutting edges. You can see the sharp edges. These are the cutting edges. These points are cutting edges. This is impinging on the surface, and see dotted lines. You can see that these dotted lines are what? These are representing the fracture. And finally, when the fracture occurs, the workpiece and the wear particles carried away by the flowing air or the gas is carried, and formation of cavity occurs. Now coming to the next slide. Now mechanics of AGM. The process is more suitable when work material is brittle and fragile. Means this AGM process is more suitable when the work material is brittle, more favorable. It will be more favorable for this process. And the MRR or Q. What is MRR? MRR is material removal rate. MRR is material removal rate. This MRR is given by the formula Q is equal to psi Z d raised to the power Q V raised to the power 3 by 2 into rho by 12 Hn raised to the power 3 by 4. Now what is Z? Z is the volume of abrasive particles impacting per unit time. How much volume of abrasive particles are impacting on the surface per unit time. D is the diameter of abrasive grains, means the grains whose size is there. What is the diameter of that abrasive? Considering that if that particle, assuming that particle is spherical, what will be the diameter of abrasive grains? V is the velocity of abrasive grains. We will know the velocity. At which velocity? As already you have seen in the previous figure, it is around 150 to 300 meter per second. Rho is the density of abrasive grains. Hn is the hardness of the workpiece. HW, it is HW. HW is the hardness of the workpiece. The flow stress means the how much hard is the workpiece, and psi is a constant. So MRR is given by this formula. Coming to the next point, very important thing is process parameter. So first is that how is process characterized? The process abrasive jet machining, how it is characterized? The process characterized by evaluated by judging the MRR, means how much material is removed per unit time, material removal rate. The geometry of the cut, what is the geometry for circular, rectangular, tapered? What is the geometry? These characterize the AGM. The roughness of the surface produced, how much smooth or rough that particular AGM process has produced, that gives the characteristics of that AGM process. Next is the rate of nozzle wear. How fast is the nozzle will wear out? Nozzle has some life hours, so it will wear out. Some have, if the material is less hard, it will wear out fast. If the material is hard, it will take, like in generally if it is hard material, it has a life hour of 300 hours. 300 hours. After 300 hours you have to change the nozzle. So the major parameters which control these quantities are, what are the major parameters? That the parameters, if you will change that parameter, there will be effect on this process. The output of the process will be affected. So for what are the process? First one is abrasive composition and strength, means what is the composition of and strength, size and mass flow rate. These all will affect the process parameters. This all will affect the process output. The gas, what is the gas? Which gas you are? Composition, pressure and velocity. The gas has some pressure, some velocity. If you change pressure, there will be effect on MRR. If you change velocity, there will be effect on MRR. The nozzle geometry, what is the geometry of that nozzle? The tip of the nozzle is circular, rectangular, tapered, trapezoidal. What is the geometry? Distance and inclination from the work surface, that is called as standoff distance. These parameters will affect the output of this process, and these are called as process parameter, which defines the performance of that process. Now the how, and now we will define one by one how. The first one is the abrasive. Now which type of abrasive is used determines the process output or the MRR. Mainly two types of abrasives are used. First one is aluminum oxide, second is silicon carbide, and size of the abrasives are in the range of 10 to 15 microns. Readily available means 10 to 50 microns, 10 raised to power 10 minus 6 or 50 raised to power 10 minus 6 meters will be the size of the grains. For good reaction on the surface, the abrasive grain should have sharp edges. Means more preferable will be grain which will be having sharp edges rather than the grains which are spherical in nature. So number of cutting edges are more, then MRR will be more. It will improve the MRR of the process. The removal of abrasive powder is normally not recommended because of decrease of cutting capacity and clogging of the nozzle orifice due to contamination. Actually, when once the abrasives have been used, it cannot be reused because it loses its cutting edge. Because of cutting edge loose, it has lower cutting capacity, and clogging of the nozzle orifice due to contamination is also because when these grains have impinged on the workpiece, what has happened, there are certain dislodged material also coming with these abrasive particles, and when they mix they create a clogging in the nozzle. So it is not recommended to use abrasive that has been used once. Now next, here you can see the effect of abrasives on MRR. So if MRR is affected, this is MRR on Y scale. If MRR is affected, the process will be affected. So mass flow rate of the abrasive particle depends on the pressure and the flow rate of the gas. Means how much mass flow rate or kg of abrasives are coming, how much kg of abrasive or grams of abrasives are coming per unit time, that is called as mass flow rate of abrasive particle depends on the pressure and the flow rate of the gas. High is the flow rate, so on the pressure and the flow rate of the gas. Second one is, so here you can see also in the diagram MRR and abrasive. The second diagram is MRR and abrasive mass flow rate. As you increase the abrasive mass flow rate, means number of abrasive particles coming out or mass of abrasive particles coming out per second is high. As it increases, MRR increases. Here you can see in the almost it is in the linear version, that as you increase the MRR abrasive flow rate, MRR is increasing. The second one is so if we increase the mass flow rate, MRR will increase. This is first process parameter. And the second one is there is an optimum mixing ratio. What is mixing ratio? It is mass fraction of the abrasive in the jet for which the MRR is highest. Means how much mass, the mass coming out having air and abrasives, how much mass of abrasives are there in that particular volume of material coming out from the nozzle. So mixing ratio is mass fraction of the abrasives in the jet. In the jet, how many abrasive particles are there for which the MRR is highest. When the flow rate of the abrasive increases, the material removal rate also increases. So here you can see mixing ratio. If you increase the mixing ratio on x-axis, if you increase the mixing ratio, MRR will increase, but after a certain level the MRR will start falling, because if you increase the number of abrasive particle, it is becoming dense. What will happen? There will be a chances of clogging, means the air coming will not be able to remove the abrasive from that place, so that fresh abrasives can attack and remove the material. So that MRR will be depending on mixing ratio, a process parameter, but in a way that it will be optimized. It is not that if you increase on going on to increase the mixing ratio, if you number of abrasive particles are increasing every moment, it is not that the MRR will be also increasing. So it is optimum. So that optimization has to be done with the mixing ratio. Now coming to the next slide, the gas and the nozzle. Now the AGM is abrasive jet machining unit normally operates at a pressure of 0.2 to 0.21 Newton per millimeter square. Pressure generally AGM operates. The composition of gas and high velocity has a significant impact on MRR. MRR is material removal rate. The composition of a gas, what gases are there, and a velocity, high velocity has a significant. If you increase the velocity, MRR will be necessarily increasing, even if the mixing ratio is not changed. Mixing ratio is not changed, no problem. But if you increase the velocity, MRR is going to be increased. The nozzle is one of the most vital. Now coming to the third process parameter, that was, first one was abrasive, second one was gas, and third one was nozzle. And nozzle is one of the most vital elements controlling the process characteristics. The nozzle material should be hard to avoid any significant wear. Means the nozzle material should be hard to avoid any significant wear due to the flowing abrasive. Normally, what is the material of nozzle? It is tungsten carbide and has a average life of 12 to 30 hours. If it is not tungsten carbide, or sapphire, if it is sapphire, which is a costly material, the life will be approximately 300 hours are used. So MRR means process will be affected if we select the nozzle. Means highly long duration of operation of a nozzle will be with sapphire, and low duration of operation will be with tungsten carbide. So according to the cost, it is adjusted according to the cost we select the material for the nozzle. For a normal operation, the cross-section area of the orifice can be either circular or rectangular, between 0.5 to 0.2 millimeter square. You can see the nozzle diameter is so small, cross-section area is so small, so the fine holes can be created on the workpiece with the help of abrasive jet machining. Coming to the next slide, nozzle tip of distance, standoff distance, a very important parameter. Now, what is nozzle tip distance standoff? It is also called as standoff distance or nozzle tip. It means distance between nozzle tip to the workpiece. Now, nozzle tip distance or the standoff distance is a critical parameter in AGM. The nozzle tip NTD means nozzle tip distance not only affects the MRR from the work surface but also shape and size of the cavity produced. Means it is not only affecting the MRR from the work surface but also shape and size of the cavity. Very important, means shape and size. If we change the nozzle tip distance, shape, whatever shape we are requiring may be produced or may not be produced depending upon the NTD. As shown in the figure in the next slide, you will show when the NTD increases, the velocity of abrasive particles impinging on the work surface increases. Why? Due to the acceleration of the particle. After they leave the nozzle, there is enough space for acceleration. So the impingement of the abrasives on the surface increases. This increases the MRR. Third point, last line, this increases the MRR. Next point, with the further increase in NTD, the velocity reduces. Now see, if you are not optimizing, you go on increasing the NTD, will not result in high MRR. And our focus is to improve the MRR, to increase the MRR so that process consumes less time with accuracy. So the velocity reduces due to the now if you further increase the NTD, the velocity reduces due to drag force of the atmosphere. Drag will come into action. There is acceleration also, but the atmospheric drag is also acting on those particles, so that will result in reducing its speed, which initially checks the increase in MRR and then decreases it. So MRR will be decrease. So you can see in the figure in the next slide, you see what is happening in the graph. You see the NTD, as we are increasing the NTD x-axis, MRR is initially it is increasing, but after certain time, certain distance, it will now stabilize and then it will start reducing. why it is increasing? It is increasing due to acceleration of the abrasive particles. And why it is decreasing? Because there will be drag force from the atmosphere. And one more thing is that you see, if you know, this is the nozzle, this is the abrasive slurry, that is abrasives coming from the nozzle. And what you can see over here is that initially this rectangular, you can see the rectangular cavity or circular cavity. It is the front view, so it is seeming like a rectangle, but it can be a circular cavity. So initially the standoff distance was 0.75 and the width of the diameter of the hole is 0.5 mm. Now in next slide you see it has been increased to 1 mm, then it has been increased to 15 mm, and then what will be the effect of that? See, what will be the it is 1.5 mm, this one is 1.5 mm and this is 2 mm. What will happen? You see there will be dispersion. This is the dispersion. Here it is straight, but now it is starting diverging. As the standoff distance is increasing, it is starting diverging. So the required shape was, what was the required shape? Required shape was this, but as you have increased standoff, what is the shape? There is more divergence, and so the shape is not exactly what we wanted. So there will be a disturbance and the shape or the contour which we wanted will not be there. So this is also the negative effect of increasing the NTD. So it has to be optimized for MRR and to get the particular. Now coming to the next slide, abrasive jet machine. Now what is that? The gas propulsion system supplies the gas propulsion system supplies clean and dry gas, air, nitrogen or carbon dioxide to propel the abrasive particles. See, the gas propulsion system is there which supplies clean and dry gas. And dry gas can be air, nitrogen or carbon dioxide to propel the abrasive particle. The gas may be supplied either by a cylinder or a compressor. Compressor can be used to supply the gas at high pressure. In case of compressor, a filter or dryer may be used to avoid water or oil contamination to the abrasive particles. The gas should be non-toxic. Yeah, this should be kept in mind. The gas which you are using should be environment friendly, non-toxic, cheap and easily available, and should not be excessively spread when discharged from a nozzle into atmosphere. So it should not spread so much. If it spreads, the shape or contour which you are requiring will not be attained, because it will spread, then the contour will be more widened. Next, this is the line diagram of AGM. The setup of, generally the setup used in AGM, how it is like, you can see this is the compressor, the center portion is the compressor, this is the compressor, and here it is the pressure gauge which is measuring the pressure. What is the pressure from the there is a relief valve. If excess of pressure is there, that has to be relieved from here. Air filter is dryer is given, so that the air or the gas coming and which is being pressurized, it is free from any dust particles or contaminations. The compressor is compressing and there is a pressure gauge. This is a opening valve. Once you open the valve, the pressurized gas moves forward, or pressurized air move. These are the pressure regulators. If you want to regulate the pressure, you can regulate according to this. And this is the air abrasive mixture chamber. Here what happens, here there is a abrasive chamber, separate abrasive chamber. From here abrasives are stored, and this is mixing in this mixing chamber. And once it is mixed, air abrasive mixture, now again there is a pressure gauge which is telling what is the pressure over here, and this is passed through nozzle, and you can see, so here you can see this is nozzle, and this is the standoff distance, and this is the workpiece, and this is a fixture for holding the workpiece. This the abrasives coming from nozzle will hit the workpiece and the cavity will be created. So this is the line diagram of AGM, or the setup diagram of AGM. Now coming to the next slide. Now abrasive jet water machining. Now we have finished abrasive jet machining, and before that we have finished water jet machining. Now coming to abrasive water jet machining. Now using only water to cut the material will of course take more time and will not be more efficient. So to make this process more efficient, what was done was that new process was developed, that is abrasive water jet machining. In water we mix the abrasives at a high pressure that used to come. Now abrasive and water both will act on the surface, and that will create the cavities at a more faster rate, at a more MRR. So this process will become more efficient. See, abrasive water jet, first point, abrasive water jet cutting is an extended version of water jet cutting. Is the extended version of water jet, in which the water jet contains abrasive particles such as silicon carbide. What are abrasive particles? As I previously told you, silicon carbide and aluminum oxide, in order to increase the material removal rate above that of water jet machining. Almost any type of material ranging from hard brittle materials such as ceramics metals and glass, to extremely soft materials such as foam and rubber can be cut. Means hard materials can also be cut and soft material can also be cut. This process is particularly suitable for heat sensitive material that cannot be machined by the process that can produce heat. So the most advantage of this process is that if there is any heat sensitive material, so that cannot be done with the help of any other process like thermal machining, which will be studying further. So for those material which are heat sensitive, this process is much better or more suitable for that type of material. Now coming to next slide, abrasive water jet, in continuation to previous slide. In this process, high velocity, what is this process all about? In this process, high velocity water exiting the jewel, that is the nozzle, creates a vacuum. Mixing chamber, jewel is a mixing chamber, creates a vacuum which sucks the abrasives. Means water is coming, and in jewel this water is coming with high velocity. If high velocity is there, there will be surrounding low pressure, and vacuum will be created which sucks the abrasive from the abrasive line, which mixes the water with slurry or with abrasives, which mixes with the water in the mixing tube to form a high velocity beam of abrasives. Now these abrasive particles have become high velocity beams. Abrasive water jet cutting is highly used in aerospace. Now where these are used, this process is used in aerospace industry. Aerospace industries. One second. Automotive industries, aerospace industries, automotive industries and electronic industries. In automotive industries, parts like interior trim, headliners, trunk liners and door panels. These headliners are there in cylinder, trunk liners, door panels and fiberglass body components and bumpers are made by this process. So whatever machining is to be done in these materials, this is done with the help of abrasive water jet machining. Now what are the advantages of AWJM, abrasive water jet? In most of the cases, no secondary finishing is required. So these processes are so fine that there is generally no requirement of further finishing process. Low cutting force on the workpiece means, as you compare with the lathe cutting the or drill bit cutting the material, it applies a huge amount of force on the work material. But in this, low cutting force on workpiece is there, so there will be no chance of creating any stress on the material. Little to no cutting burr. There is a burr are the burr you can if you don't know, the burrs are what, I show you. The burrs are like, if this is the material, and while if it has been cut from this workpiece, what will happen, there will be small burrs to the edges of these are called burrs, small edges. So in this process what will happen, there will be no burrs, no heat affected zone. As there is no thermal energy involved, there will be no heat affected zone. Localizes structural changes only very near to the deformation, there will be structural changes, and there will be no widespread structural changes over the whole of the material. Eliminates thermal distortion. So if there is no thermal energy involved, there will be no thermal wear and tear, no thermal distortion, thermal stresses will not be there. No cutter induced metal contamination. If you see in normal cutting, lathe cutting, what happens, there is contamination of tool material to the workpiece. So the characteristics of the workpiece may change to some extent at that local points, but in this case there is no cutter induced contamination, means there is no direct tool contact, so there is no contamination on the workpiece. Now if this process has certainly advantage, there are certain limitation with this process. The major disadvantage of abrasive jet water cutting or water machining, AWJM, are high capital cost. Initial cost of setup is very high, and high noise level during the operation. During the operation it creates a lot of noise. So it cannot drill flat bottom. Now what do you mean by it cannot drill flat bottom? See, like if you, this is the workpiece, and if you want to drill the here, so this is called flat bottom, but in AWJM it is not possible to dig the flat bottom. Instead of that, you will get a bottom of this shape. It cannot be flat because the abrasive particles are hitting, and it cannot create a flat bottom because there is no flat tool involved. So abrasive particles will hit, and it at the center it will be more deep, and at the as you go away from the center there will be less deepness, and so it cannot create a flat bottom. Cannot cut materials that degrades quickly with moisture. So moisture is there, so any material which is affected to moisture cannot be cut with this process. Surface finish degrades at higher cut speeds. If you increase the cutting velocity, the surface finish will degrade, which are frequently used for rough cuts. So high speeds are generally used for rough cuts. If you are increasing the high or increasing the velocity, the surface finish will be compromised. So this is the limitation of this process. Now this is the schematic of a abrasive jet water machining. Here you can see how it sucks the cutting particles or abrasives from the, so this is the water jet. This black line is what it is representing. It is representing a water jet, this black line, and this is the trajectory of an abrasive particle. What happens, this is called jewel or nozzle or the mixing chamber. So this is the mixing chamber, this is the water jet, black one, water jet, mixing chamber. This abrasives are coming from abrasive line, this water is coming from pump. So here what happens, the water is flowing with a high velocity. What it is creating, if it is flowing with high velocity, there it is creating a low pressure area. So what will happen, these abrasive particles will slowly align to this water due to low pressure area. Low pressure, it will come to the center, and finally it will be in stream with water, so creating a abrasive stream. This is a schematic of a abrasive water. How it works, how abrasives are mixed in the water stream is shown in this diagram. Now we would like to end this lecture over here, and from the next lecture we will be studying the ultrasonic machining. Thank you, students.